Okay, think about this for a second. Something like 95% of the food we eat, it comes directly from the soil. That's, the very foundation.
It really is, and it's under enormous pressure.
Exactly. Because we're looking at needing, 35 to maybe 56% more food production globally by 2050? That's huge.
It's a massive challenge.
And we hear a lot about erosion, maybe overuse of fertilizers, those kinds of soil problems. But today, we're doing a deep dive into something maybe less obvious, but really critical.
Toxic heavy metal pollution in soils.
Precisely. And this is, it's vital stuff for anyone tracking environmental security, sustainable agriculture, and I'd say particularly relevant if you're a UPSC aspirant, right? Grappling with these exact policy areas.
Absolutely. Understanding this is key for resource management, environmental policy, food security, all interconnected.
So we're going to unpack some pretty eye-opening findings today.
We are, and we're basing this on a really comprehensive study, not just a small snapshot.
Right, this isn't just one local area.
No. This is synthesizing almost 800,000 soil concentration data points. Think about that number, from nearly 1,500 different regional studies all across the globe.
Wow.
Yeah, recently published by DTE in Science. It gives us a scale of understanding we haven't really had before.
Okay, so our mission today is clear then. Let's pull out the key insights from this massive study.
Let's do it. We need to understand how bad this toxic metal contamination is, globally speaking.
Where it's coming from.
The sources.
And why it's distributed the way it is, what drives that pattern.
And ultimately, what does it all mean? The potential impacts on, food, our health.
Exactly.
All right, let's get into it. Soil degradation, like we said, it's known. But toxic metals, it feels more, insidious.
It is, because unlike, say, organic pollutants, these metals, we're talking arsenic, cadmium, copper, nickel, lead, chromium, cobalt.
The usual suspects.
Pretty much. They don't just break down and disappear over time.
They stick around. They persist. They can build up, accumulate in the soil for decades. It's a long-term, kind of silent threat building up.
And even metals we need tiny amounts of, like copper or cobalt, they can become toxic too.
Yes, absolutely. If they get too concentrated, especially as they move up the food chain, that's called bioaccumulation, they become toxic.
Okay, so what's the big picture then, this huge data set? Does it show this is just pockets here and there, or is it more widespread?
Well, the study's global estimates are, frankly, alarming. They reckon that somewhere between 14 and 17% of surface soils in cropland areas.
So land used for growing food.
Exactly. They exceed the agricultural safety thresholds for at least one toxic metal.
14 to 17%. That doesn't sound like a small number when you think about all the world's farmland.
It's not. It represents a massive area struggling potentially to produce safe food, possibly impacting yields, needing costly cleanup later. It's a genuine threat to food supply stability.
And what about thresholds for, like, general ecological health or direct human health?
Even looking at those thresholds, the exceedance is still significant. Around 6.8%, still a major concern.
That's a big slice of our food-producing land. Are certain metals popping up more often than others as the main culprits?
Yes, definitely. Cadmium shows the highest rate of exceedance. That's at 9.0%.
And cadmium is particularly nasty, isn't it?
It is. It's a known carcinogen, and it gets taken up pretty easily by crops, things like grains, leafy vegetables, so it gets into the food chain quite directly.
Okay, so cadmium's the biggest one. What else?
Nickel and chromium follow, with exceedance rates of 5.8% and 3.2% respectively.
And does the study pinpoint specific regions like hotspots for these?
It does. For cadmium, areas like northern and central India, Pakistan, Bangladesh, and also southern China show heightened levels.
Okay.
For nickel and chromium, it's more the Middle East, parts of subarctic Russia, and eastern Africa.
And arsenic. I know that's a big concern in some areas.
Yes. For arsenic, the hotspots identified are southern and southwestern China, and also across South and Southeast Asia.
So it's quite variable geographically. Where are all these metals actually coming from? Is it all industrial, or is nature playing a part too?
It's definitely a mix. There are what we call geogenic sources, that just means natural geological sources.
From the rocks themselves.
Exactly. Metals are naturally present in the Earth's crust. When the parent rocks the soil originally forms from weather over time, they release these metals.
So like volcanic rocks or certain sedimentary rocks.
Precisely. Rocks like basalt and shale, or minerals like pyrite, they can naturally have higher concentrations of arsenic, cadmium, copper, nickel because of their chemistry. Weathering just breaks them down slowly.
Okay, so there's a natural background level we have to consider. But I'm guessing human activities have ramped things up.
Oh, significantly. Anthropogenic or human-caused sources have really amplified the problem. This goes way back, actually, starting around the Bronze Age with the beginning of metal mining and processing.
Right, digging this stuff up.
Yeah. Mining brings huge amounts of metal-rich rock and ore to the surface. And the waste from that, the tailings, the waste rock, can then leach metals into soil and water when it rains.
And wind can blow the dust around, too.
Yes, wind erosion of mine waste is a factor. And also atmospheric deposition, tiny particles released from smelters traveling through the air and settling back down onto the land, sometimes far away.
It's amazing how far it can travel.
It really is. They've found evidence of pollution from ancient Greek and Roman mining activities trapped in Greenland ice cores. That shows you the long-range transport and just how long this human impact has been going on.
Wow. That puts it in perspective. What about more modern sources today?
Well, today you've got modern industrial infrastructure, obviously, but also agriculture itself contributes.
Also.
Phosphate fertilizers, for example. They're essential for crop yields, but they can contain trace amounts of heavy metals, like cadmium, as impurities. Use them year after year and it builds up.
Right. And other things.
Yeah.
Like waste.
Definitely. Things like paints, batteries, electronic waste, if they aren't disposed of properly, they can leach metals. And a big one is irrigation, especially using water that might be contaminated by industrial wastewater or runoff. That's a direct pathway onto farmland.
It sounds like a really complex web of sources. So, okay, we know where they come from, roughly. But why do they end up concentrated in those specific patterns the study found? What drives the distribution?
Right. It's not just about the input. It's also about how metals move around and leave the soil system. It's a dynamic balance.
Inputs and outputs.
Exactly. Metals can be removed or output through leaching, where water carries them down deeper into the soil, maybe into groundwater,
Right.
or through soil erosion, washing away the topsoil. And also, plants take up metals.
And then we harvest the plants.
Right, so that removes some metals from the field.
Yeah.
But there's also redistribution within the soil.
How does that work?
There's something called the plant pump effect. Plants, especially deep-rooted ones, draw up water and nutrients from lower soil layers, but they can also pull up these metals dissolved in the water.
Ah, okay. Then, when the plant sheds leaves or eventually dies and decomposes on the surface, those metals it pulled up from deeper down get concentrated in the topsoil. It effectively pumps them to the surface.
That's fascinating, like tiny biological conveyors.
Sort of, yeah. And then on a bigger scale, regionally, metals can move through things like biovolatilization. Some microbes can turn metals into gases. Wind can carry soil particles with metals attached. Even forest fires can release metals into the atmosphere.
And the study used machine learning to try and untangle all these environmental factors, didn't it? What did the models find?
Yes, they did. And they found some really interesting correlations, factors like near-surface temperature, rainfall, and evapotranspiration, basically. How much water evaporates seemed to have a positive correlation.
Meaning higher levels of those lead to higher metal concentrations.
Generally, yes. In places like southern China, India, the Middle East, Central America, Central Africa, the thinking is that warmer, wetter conditions accelerate chemical weathering of those parent rocks, releasing metals faster. Okay, that makes sense. What about factors that reduce concentrations?
Well, things like ground frosts and having lots of wet days showed a negative correlation. Maybe because freezing slows down weathering, or frequent rain leads to more leaching, washing the metals out of the topsoil more effectively.
So climate plays a really significant role. Did they highlight any specific climate zones?
They did. The subtropical monsoon climate stood out. These areas are obviously vital for agriculture globally.
Right, lots of major food production there.
And they showed a significantly higher metal exceedance rate, 34% for those agricultural thresholds we mentioned. It seems that combination of high heat and strong seasonal rain, even with a dry period, creates conditions that really favor metal enrichment in the soil.
Interesting. Any other landscape factors?
Yes, higher elevations and steeper slopes also correlated with higher exceedances, probably linked to faster weathering, different soil formation processes, and maybe being more prone to erosion concentrating metals in certain spots.
So a lot of natural environmental drivers.
Yeah.
But it wasn't just nature, right? The study also pointed to socioeconomic factors.
Oh, absolutely critical. The models found that indicators of mining intensity were the strongest socioeconomic predictors.
Like what kind of indicators?
Things like the value of ores and metals being exported or imported, how much a country relies on mineral rents, the rate of mineral depletion. These factors strongly predicted higher toxic metal levels.
So that really confirms the huge legacy of mining and smelting.
It really underscores it, yes, globally. Another strong predictor was the proportion of land that's irrigated.
Which connects back to what you said about contaminated water.
Exactly. It reinforces that link between industrial or urban water contamination and subsequent pollution of farmland via irrigation.
Is there anything surprising there?
Well, maybe that irrigation using groundwater generally predicted lower exceedances.
Oh, why would that be?
It's not entirely clear, but perhaps groundwater is often less directly contaminated by surface industrial activities compared to rivers in many areas. But there are exceptions, of course, especially in areas where the groundwater itself is naturally high in certain metals, like arsenic, or where there's specific groundwater pollution happening.
Okay, now the study talked about this metal-enriched corridor across Eurasia. That sounded particularly significant.
Yes, that was a really compelling finding. They identified this major high-risk zone stretching across low-latitude Eurasia, dipping into southern Europe, covering the Middle East, South Asia, and southern China.
And the striking thing was the historical overlap.
That's what's fascinating. This corridor matches up remarkably well with the heartlands of several major ancient civilizations. You know, the Greek, Roman, Persian empires, ancient India, the early Chinese cultures along the Yangtzes.
That's quite a coincidence. Or maybe not a coincidence.
Probably not. The researchers suggest it's likely a combination of factors coming together over a very long time.
Like what?
Well, first, the underlying geology in these regions might have been naturally richer in some of these metals to begin with. Then, the climates promoted strong weathering, releasing those metals.
Nope.
Add in that plant pump effect we talked about, concentrating metals in the topsoil over millennia. Maybe in some areas, lower rainfall limited leaching, so the metals weren't washed away as much.
And crucially,
These were precisely the areas where early intensive mining and smelting took off, thousands of years ago in some cases. So you have this long, long history of human activity layering pollution on top of those natural predispositions. It's a legacy written into the soil.
that really paints a picture, a concerning one. So what does this all mean today? What are the actual quantifiable impacts of this pollution on food and health?
Well, the study put some numbers on it. They estimate around 242 million hectares of cropland worldwide are affected by these toxic metal exceedances. That's about 16% globally.
16%, and the regions most at risk.
Again, highlighting southern China, northern and central India, and the Middle East. They do caution that the data for Africa is patchier, so the situation there might be underestimated.
And in terms of people living in these high-risk areas?
The estimates are stark, somewhere between 1.9 and 1.4 billion people.
A billion people. That's incredible. But risk isn't just about living there, right? The study mentions other factors.
Exactly. It's complex. The actual risk to health depends on many things. How mobile are the metals in that specific soil? How bioavailable are they, meaning how easily can plants actually absorb them? And then how easily can we absorb them from the food?
And our diets matter too, presumably.
Hugely. Dietary habits, how much local produce people eat, whether people are already suffering from malnutrition, which can affect metal absorption, and also the risk from multiple metals combined might be worse than just one alone.
Synergistic effects.
Potentially, yes. And another point they raise is international food trade. Contaminated food doesn't necessarily stay local. It could potentially spread these risks much more widely.
Right. And looking forward, is this problem likely to get better or worse?
Well, the study offers a rather sobering perspective here. The global demand for many metals is actually projected to increase,
Why is that?
primarily due to the transition towards green technologies. Think solar panels, wind turbines, electric vehicle batteries. They all require large amounts of various metals, including some of the ones we've been discussing.
So the very technologies meant to help the environment could actually drive more mining and potentially worsen soil pollution.
That's the potential paradox, yes. Increased demand could lead to more mining, more processing, and potentially exacerbate this problem of toxic metal enrichment in soils if not managed extremely carefully.
Okay, so let's try and recap this deep dive. Based on that DTE and science study, we've seen there's a really significant global problem with toxic heavy metals in soil.
Yes, affecting a large percentage of cropland.
It's driven by both natural geology and, importantly, a long history of human activity, especially mining, industry, and even some agricultural practices.
And the distribution isn't random. Climate, landscape, and socioeconomic factors like mining intensity create these patterns and hotspots.
Including that metal-enriched corridor with its deep historical roots. And the potential impacts. Serious concerns for food security and the health of potentially over 1 billion people.
That sums it up well. And for you, the listener, especially if you're preparing for UPSC, really understanding this complex interplay is vital.
Yeah, it touches on so many syllabus areas.
Sustainable agriculture, definitely. Industrial policy, environmental law, public health initiatives. They're all connected through issues like this one. It gives you a much more nuanced perspective.
It really does. And it leaves us with a pretty challenging thought, doesn't it?
Yeah.
Given that this pollution lasts so long and our demand for metals is actually growing, how do we balance that?
How do societies balance technological progress, the need for these metals, with the absolute necessity of protecting our soil, this fundamental resource?
What policies could work? What individual actions might help? It's a huge question to ponder.
It certainly is. There are no easy answers.
Absolutely. Well, if you found this deep dive helpful and you want to keep exploring these kinds of critical environmental and policy issues, please do give us the like, subscribe to the channel.
And leave a comment. If you have more questions or your own thoughts on tackling soil pollution, we'd love to hear them.
And remember, this discussion was based on that significant research published by DTE and Science. Definitely worth looking into their work further if this topic interests you.